sigma 1, 1 times N1, right? Plus sigma 2, 1, but now let me use this, the symmetric property of the tensor. So it's going to be sigma 1, 2 times N2. And again, I use the symmetric property of the tensor, sigma 1, 3 times N3. And you can do exactly the same thing for T2 and T3, and you will find that the vector that results, the stress vector that results in the projection of stress on an arbitrary plane is going to be the product of the stress tensor times the components of the vector normal to that plane. And we can summarize this. So let's call this equation 3. We can summarize this as T, stresses T is going to be equal to the tensor sigma times the vector n. But this is not the end. We need to do one more thing. Notice that here we're getting a vector of stresses, right? So, and what I was asking you before was not to compute the vector of the stresses, but to calculate, where is that copy that I had before? It was the shear stress and the normal stress, right? I lost my copy. I don't know where it is. Okay, but what I wanted you to compute was normal stress and shear stress. So how do I compute normal stress? Notice that T is not necessarily aligned with N. So if I wanted to get the component normal to the plane, what do I have to do? You could multiply times the sign, right? But in vector, with vector operations, what would you do? You will do a dot product, right? So you need to multiply this T one more time times N. Notice that we have defined T in this case. Well, I did it with the sigma. So very well, this should be sigma n. Sigma n, as I have defined over here, is going to be T times n. And what about shear stress? What is shear stress going to be? The shear stress, notice that we know the direction of the normal stress because it's perpendicular to this plane. But shear stress could be here, there, it could be in any direction. So let me not go into, it's going to have two components, the shear stress. But let's just talk about the module of that. And the module of shear stress is going to be, as you said before, the magnitude of T squared minus sigma n squared. This is going to give you what is the magnitude of the shear stress. We don't know the orientation yet, okay? But with this formula, you could compute what are the normal and shear stresses in 3 dimensions. So this is basically everything you need in 3 dimensions, okay? So in 3 dimensions, no need of playing with more circles, anything like that. As soon as you have the orientation of your plane and you have your stress tensor, you just do that multiplication and that's it. Looks simple, right? But it's not that simple because we need to do a few more things. Theoretically, this is it. That's it. That's the end. That's all you need. But in practice, we need to take a few more steps. remember that in practice, let's see if now I find the page I was working on. No, I don't see it. In practice, we define the orientation of planes respect to the north. We define the dip of a plane respect to a horizontal plane. In practice, we define the orientation of stress respect to the north or to some geographical coordinate system. This is the key word that you need here, azimuth. It refers orientation from the north. So now we need to tie this to some geographical convention. So as soon as we know our principal stresses for an arbitrary direction, we can compute the normal shear stress for a plane given also in a geographical coordinate system for an arbitrary direction too. So in order to do that, we're going to adopt a convention of coordinate systems. And we're going to use what I call the geographical coordinate system. In the geographical coordinate system, we're going to stick to some conventions like what we call north, what we call east, and we're going to do one more. We're going to add a coordinate system which is D, which is, you could say stands for depth. Okay. For this coordinate system, it's also going to be a right-handed coordinate system. Okay. And you will see this is going to be very useful when we refer to stresses in an arbitrary direction on a fault or on a fracture, or also for deviated wellbores. We're going to come back to the same coordinate system. The first element of this coordinate system, of the geographical coordinate system, is going to be n. So if n is the first element, can somebody tell me what's going to be the second element? So n is going to be your index, right? E is going to be the second one, and D is going to be the third one. So that's going to be the NED coordinate system. However, when you go to the field, usually you don't say principal stress is 35 degrees, or let's do something more complicated. Minimum principal stress is 134 degrees from the north. No, you don't say that, right? Probably you will find something easier to refer your orientation of stress, and you're going to refer it eventually to the north, but you're not going to write your stress tensor directly in this coordinate system. First, you're going to write it because that's what we're going to measure in the field too, principal stresses, not the stresses in this system. So let's imagine, let's do a simple case, okay? I'm going to write here the same coordinate system that we had before, NED, but let's say that our maximum principal stress is at an angle from the north. And just for simplicity, let's assume that one of the principal stresses is still vertical. So let's say that this is S1, this is S2, and this is S3. So let's check if this right-handed coordinate system. It has to be, otherwise this is not going to work. So this is 1, you do like that, right? It's going to be 2, it's going to be 3 going down. So this is how you report your principal stress system. Here, from the principal stress coordinate system, you could write your stress tensor, say SP, equal to S1, S2, and S3. And you could say, in addition, let's say for this example, that S1 is at, let's say, 30 degrees from the north, okay? Actually, this at 30 degrees is something called the azimuth of S1. It's measured from the north, always clockwise. And I'm going to say also that S3 is vertical. So I have 3 values of principal stress. I have 2 directions of the principal directions, and the third one is automatically defined. So we need anything, we have everything we need to fully characterize that stress tensor respect to the coordinate system. So what do we do now? In order to have our stress convention to talk to our fault convention for orientation, we need to write this stress or principal stresses in the geographical coordinate system. And what is that stress tensor going to look like? Anyone can tell me? So remember that this is, of course, right-handed coordinate system, right? S1, S2, S3. It's not that easy to calculate. And actually, I'm not going to write it down here, but I have uploaded the full equation for that. I'm going to put it up in the screen in a sec. But it's just a change of coordinate system in which SG is going to be equal to a rotation matrix going from the principal stress coordinate system to the geographical coordinate system transpose times that tensor that we know how it looks like times the that same matrix that it's a rotation matrix, where RPG is going to be a 3x3 matrix in which each of these elements is going to be a function of some angles that we're going to define as alpha, beta, and gamma. So let's talk about the RPG matrix. As I was telling you, I'm not gonna write it because that doesn't make sense. It's a lot of writing, and I already have it here. And even for you, you just have to code it once. Once you code it, you don't have to write it again. So let me go over here. This is actually something that I do not cover in the undergraduate classes, so you're not going to find it there. I'll try to add it if I have time, but it looks, okay, let me change this. If you go to Files, and you go to this file, number 2, don't worry about number 1. Number 1, actually, now it's incorporated in the undergraduate notes. Let me download this. So this is a this is basically the same we have been saying before, right? Random orientation of fractures, all of those state of stress are going to fall somewhere in here. this is a better explanation for the strike and dip. Remember, the dip is going to be always an angle from a horizontal plane to the plane that you're considering. So in this case, it's going to be this angle. It's easy to think that plane as if, for example, you have water, right? And that plane is going to be the plane of the water. And the strike is going to be the angle between the north, let's say the north is in that direction, and the line, which is intersection of a horizontal plane, which in this case is the water, and the plane that you're considering. So two planes make a line. That's the line of the strike. And that's going to be a horizontal line. The angle between the north and that line, that's going to be the value of strike. Always measure clockwise from the north. There is some other notation for azimuth. And usually this is what the geologists use. It's easier to work in the field, but when we're just doing math, this is much better. So just use this convention that you see over here. And as I was telling you before, always the angle clockwise to that line. We'll see later on, you will say, oh, but which line do I pick, this one or that one? Well, that's going to depend also on the orientation of the fault. We're going to see that in a bit. And the dip, we already talked about the dip. So dip of 0 degrees, horizontal angle. Dip of 90 degrees is a vertical angle. And this is what you see in maps, geological maps, when you see dip. And we already talked about this. And we were starting to talk about that, right? So this is our matrix of principal stresses. For an arbitrary condition. Now it's not necessarily aligned with 1, 2, 3 or with NED. It's an arbitrary state of stress. When you write that state of stress in the geographical coordinate system, it's going to look like that. It's not going to be as easy like that. Now it's going to have off-diagonal terms. So I have an analogy for that. And actually, that's why I bought this cube. Let me see if I can make this work. So the state of stress always is going to have 3 principal directions, right? But that doesn't mean that you're going to always, your coordinate system that you choose is going to be oriented with those principal directions. So having a coordinate system which is not oriented with the principal direction, it's like looking at this cube like in some random orientation in which the planes do not coincide with those directions, right? There are just going to be 3 directions in which if you look in that particular orientation, you're going to see through and you're going to have the value of, that's going to be a principal direction, that's going to be your principal stress value too. So that's going to be 1, right? There's going to be another, and that's going to be another. So my idea was to, I think I can't see any more, but was kind of to paint like this side, like red and red, blue and blue, green and green, just to see that when you look at this at an angle, you have a combination of colors. You don't have like the main color, right? But when you look in a given direction, which is the direction of the principal stress, you see only that color. And it's the same thing with principal stresses, principal directions. What?
You should probably shine a laser through it.
Put a laser.
Yeah, so if you shine the laser on the face, if you're looking at the face, the laser pointer is going through the straight through line, versus if you're looking for a different angle, you'll see it refracting around using the
Probably. I'll try that. I think I have a laser downstairs. Okay, so in order to go from here to there, we need that matrix. And that matrix RPG is going to be a function of the angles alpha, beta, and gamma. So what are alpha, beta, and gamma? This is just a convention, okay? The matrix is composed by the projections of elements of one base on the other base. That's how it works mathematically. And that's why you have these cosines of alpha, beta, and gamma. So, and according to this convention, alpha is going to be the angle, the horizontal angle between the north and the projection of x1 or principal direction 1 on the horizontal plane. You see, is that this angle over here. Beta is going to be a vertical angle from a horizontal plane to x1. And look that if you were to fix x1, right? x1 index finger, x2 is the middle finger, and x3 is the thumb. You can fix what is the value of x1, but still there is one more variable, which is this gamma. So gamma is going to be the angle between the horizontal plane and vertical angle between the horizontal plane and x2. With those three angles, you can fully define the orientation of x1, x2, and x3. I'm not going to go in detail to all the examples because we're running out of time, and I have already prepared some examples for you according to the orientations of the stresses. Either if you have normal faulting, it's going to be a much simpler version of alpha, beta, and gamma. If you have strike slip, here you have the example, and also you can verify your code with the results over here, or if you had reverse faulting. Okay?
Gamma is also a vertical angle, right?
Gamma is
X2 below
a vertical angle. Yes, it's a vertical angle between x2 and a horizontal plane. And if you want even, well, we'll get this in a sec, but if you want a little bit more of animation, I'll recommend that you go and you visit this link. You go to projects, number 2. Professor Foster actually prepared one of these widgets that allow you to see how, if you vary alpha, beta, and gamma, that the orientation of those elements is going to vary. But you will see for your case, which is, I don't remember what is state of stress at depth E, but I think probably it's reverse from the previous project. Let me just check that in a sec. So depth E, yeah, it's reverse. The maximum vertical stress is horizontal, and the minimum principal stress is, well, no, it's not reverse. It's strike slip. It's strike slip. So for that one, you can just go to, well, we wait that that one builds. So this is Firefox, right? Yes. So it should work. You just go to this case, and the only variable is going to be the azimuth of SH max, which is going to be x2. If you know what is the azimuth of SH max, you also know what is the azimuth of SH min, your orientation with respect to the north, and you're going to be able to solve it. Okay, let's see if that's already okay. So it's working or not? Okay, still building. Okay, let's let the computer work a little bit. We need one more thing. So now, you have SG, but we need now to define what is N, the vector of the fault. And for that, we're going to define another coordinate system. So we use the same coordinate system, right? NED. I'm going to write it on top of this. North, east, depth. But now we were interested in an arbitrary plane with a given strike and a given dip. So that's a plane. Can you see it's a plane? Which is it's not aligned with any of the other directions. Well, here also we're going to define three vectors. And this is going to be the D, S, N coordinate system. So the D is going to stand for a vector which is on the plane, and it's going to be called ND, and that comes from, the D comes from deep. This one is going to be NS, and the S comes from strike. And the third one, which is the cross product of these two, is going to be the normal, and it's going to be N, right? So all those are vectors. And as long as I write those vectors on the coordinate system NED, I'm going to be able to write what is NN what is ND and what is NS. Actually, I'm not going to put the values here, so don't worry about the space. Just want to make a point that these are vectors. So what is the value of NN? I don't remember, so, and I don't know that by heart. So let me come back to the computer, and this is, okay, it should be working. All right, I'll come back to this one. But let me come back to my presentation. Now that we can calculate what is SG for an arbitrary case, now we need to know what is NN, NS, and ND. And NN is going to be that. Okay? So again, sine and cosines, and where the strike is the angle between the north and the strike of the plane, and the dip is going to be the angle between a horizontal plane and, you could say, ND, or the plane itself, on the direction of the maximum slope, of course. And after you've got all this, now we can do what we did before. So remember, our equation was sigma, what we said before, T. It was sigma n times n. That was the equation that we derived before. Let me add here a prime, just to mean that that's effective stress. With SG and with NN, I can compute SN is going to be equal to SG times NN, and from here I can further compute what is sigma n, which is going to be Sn minus, no, this is wrong. This is T. I was going one step further. And this is a vector. So sigma n is going to be, well, let me before I don't want to save steps here. So Sn is going to be T dot product Nn, and sigma n is going to be Sn minus the pore pressure and tau is going to be square root of t squared minus sigma n squared. No, but this t should be Sn squared. And that's it. That's everything you have to do for to solve the problem of stress projection in an arbitrary plane. It's very important here that you consider the orientation of a geographical coordinate system in order to be able to use the two data sets. Yes, person.
Can you do it very, very quickly? So, what's what?
Here?
Yeah. Or just what variables mean what? Is like, where is Sn?
So, Sn, this is the total normal stress on the plane, on the arbitrary plane that we have chosen, which is that one over here. This is the effective normal stress. And this one is the shear stress. So in order to close the loop here, when you plot your 3D Moore circle, in the case that for that example in the vaca morta formation, at some point you're going to have sigma h max. It's strike slip, so sigma h mean is going to be the minimum, and sigma b is going to be somewhere here in the middle. This is going to be your 3D Moore circle. And the shear stress and normal stress at an arbitrary location is going to be sigma n and tau given by the equations above. Yes?
So if I start even if I start in the principal stress coordinate system, if I start with the effective stress, so I've already subtracted both.
Yes,
and then
correct.
matrix,
Yes.
I'm going to get the effective stress.
Yes, yes, correct. Yes.
That's what that T prime is.
That's what the T prime is, yes.
Effective.
Yes. Yeah, you can go either way. I'm sticking to this one because that's what I have in the notes. So let me come back to the computer over here. That's what I have in the notes. And this, you see that there are some characters that are not showing very well. I have to correct that. I have to work on that. But the most important thing here is NN, NS, and ND. That's the definition. If you use that, it should work. And I think here I have some examples too that you